Chapter 2 of General Chemistry 1 deals with atoms, ions, and molecules. This will be a sample quiz that is worked through for solutions either for a learning purpose or for a review for an exam. So let's dive right in. When Rutherford shot alpha particles at a thin piece of gold film, most passed straight through, but some were reflected or repelled. The conclusion drawn from the experiment was what? And this is the gold foil experiment. Obviously, Rutherford is not a guy who really had much to do with electrons. That was more J.J. Thomson and Millikan with his oil drop experiment. And this is just knowing from the facts that we learned from our lecture series and from textbook. Obviously, it has nothing to do with density. We said electrons were crossed out because it has to do with more of nuclei and nucleal properties. And the reason, remember, is because those nuclei of the gold atom sometimes would align just right as to when they bounced back. So obviously the nucleus occupies a very small part of the volume of an atom, and that is because it's really hard to pick out where exactly it is, but it's somewhere in that area, right? And obviously different isotopes exist, have nothing to do with where the nucleus is. Based on the path that they follow, which one of the following is being shot through the electric field shown at the right? Now we're seeing that it's bowing up towards the positive charge, right? If it's attracted to positive, it's going to be negative. Right? And our negative charged particle is an electron. Okay. What is the common name for the elements in this group? We're talking about the groups of the periodic table. So one would be the alkali metals. Wow. Wow. Leave it to me to spell it wrong. There we go. And 17 would be the halogens. Moving on. Elements were originally placed into the same column or group on the periodic table because they had similar masses, same number of protons, same number of neutrons, or similar chemical properties. Let's be real. The only reasonable answer in this is B. And that is because as we move up in atomic number, we move up in protons, which means we move up in mass, which means we also move up in the number of neutrons. So that kind of rules out A, D, and C right off the bat. So we're completing the table here. Here we go, right? So we need to fill in a symbol, and we need to fill in some protons, and on occasion, a neutron. Let's do it, okay? For iron 55, obviously iron is number 26 on the periodic table, so it has 26 protons, okay? Since there's no charge on it, it's neutral. That means we also have 26 electrons, okay? The mass number is found right here, so we're going to chuck a 55 down in mass number, okay? And now all we have to go is 55 minus 26, which is 29, and put that up in number of neutrons. Moving on, we know that it has 12 protons, and element number 12 is magnesium, so I'm going to put an Mg down there, okay? Now, if there are 12 protons and 10 electrons, right, that means we have a surplus of 2 protons, which means we have a 2 plus charge. We already know that we have a mass number of 27, so we can write a 27 up here where that mass number goes. And all we have to do then is say 27 minus 12, right, mass number minus 12 protons, right, equals 15 neutrons, right? Remember, our mass number is just our protons and neutrons added together because they are accepted to have the same technical mass. The Fermi 1 fast breeder reactor used enriched boron in its control rods. Determine the average atomic mass of the enriched boron. Remember that all we are doing is multiplying our mass by the percent as a decimal of how much of it is there. So let's do that. Okay. In one type of boron, we have a mass of 10.013 atomic mass units at a percentage of 31.67. A second isotope has a mass of 11.009 AMUs at an abundance of 68.33%. So let's do it. So we are going to say we have, right, 10.013 AMU times, this is a decimal, right? Our percent as a decimal, right? Times 0.3167 plus, right? 11.009 AMU times 0.6833, right? And actually, that just gives us our answer right there at 10.69 AMU. Now, a common mistake, right, is people will divide that by 2. Okay? You don't need to do that. You don't need to average them, right? That's not what we're doing. We're already ironing out that the percentages, right, will add up to 1. If the percentages add up to 1, we have the same amount. We're not doubling it, right? We're still staying at 100% total. So there's no need to divide by anything. Once you multiply by those percents as decimals, by the correct mass of the correct isotope, you're done. Okay? We're going to do some naming, and that's pretty much it for the rest of this. Every good chemistry student knows that ammonia, I hate how big that is. Every good chemistry student knows, right, that ammonia is a weak base. Just a hint for chapter 4. So remember, ammonia is one of those ones that you just have to know. Okay, so just memorizing. Right? In letter B, we have a sodium cation and a ClO minus, right? That's technically Na plus and ClO minus. The name for ClO minus, right, is the hypochlorite, even less oxygens than regular chlorite, which is ClO2 minus. So it is ionic compound. So name of the cation, sodium. Name of the anion, hypochlorite. And sodium hypochlorite is actually what is, or at least what is in some bleaches. Cool. So again, name of our cation, name of our anion. Obviously we have a magnesium cation. This forms a 2+ cation because to get to the most previous noble gas, right, it's in group 2. It has a +2 charge. So, and this is all stuff that you'll learn later in the course as well. But just remember, group 2 of the periodic table, +2 cation charge. And then this NO3, right, which has more oxygens than its little brother anion, NO2. So we'll have that ATE ending. So we will have magnesium nitrate. And it is not dinitrate, okay? Di prefixes, tri, mono, tetra, only for molecular compounds, okay? These are all ionic. This is molecular. Right? Okay. Last ionic compound. Okay, we have CuS. Remember, when those pure elements are anions, it's just that IDE ending. So this is sulfur. We're going to chop off that UR off the end. We're going to add an IDE. So we have sulfide anion, and then we have the copper cation. But more specifically, we know that copper is a transition metal. It can have a charge of +1 or +2. Okay? And since there's only one sulfur tacked on there, and there's only one copper tacked on there, right? Sulfur, as an anion, the sulfide anion, only ever has a charge of 2-. So we know that our copper has to have a charge of 2+. Since this is a transition metal, we have to indicate the charge. So we're going to say it's copper 2 sulfide. Or you can use the other naming system, right? And you can say it's cupric. IC ending, right, for the higher charge. Okay. Now we have our molecular compound. This one's so easy, right? There's a 2 on nitrogen, so there's a di prefix there. There's a 3 on oxygen, so there's a tri prefix there. So it is just di-nitrogen. Wow. I was thinking ahead to trioxide, right? Right. Dinitrogen trioxide. Moving down. Okay. Now we're writing formulas, so we're going to start writing some charges up there. Now, iron 3, we know is a 3+ charge. Okay. Sulfate, ATE, a good way to remember sulfate, right, is to remember sulfuric acid, H2, need 2 protons, right? Sulfate is a 2-. Okay. So we will have Fe2SO4 3, right? So 2 times the 3+ gives us 6+. 3 times the 2- gives us 6-, so we're nice and even. Potassium has a charge of 1+. Chlorate, ClO3-, right, has a charge of -1. So we're all balanced already, so all we have to do is write out our cation next to our anion, and we are done. We are done. Okay, now there's a molecular compound, so all we're going to do, right, is we have di and we have hept. So we're just going to write Cl for chlorine, a little 2. Actually, let me move this up. Cl for chlorine and a little 2, right? And then an O with a little 7. Now let's make sure your 2 and your 7 look different. It is possible for them to look similar, so just be careful of that. And then really quick, remember this hydrate is just a little dot, so times, and then X being your prefix, and then H2O, right? So we have calcium and bromide, okay? Bromide, calcium, so bromide has a charge of -, calcium has a charge of 2+. So we have CaBr2, right? And then we remember our hexahydrate times 6H2O. So this has been the Chapter 2 walkthrough. I hope this was helpful to you, whether you use it for studying or whether you use it for more of a lecture style. If you have questions, obviously contact your professor or other students you value as dependable sources.